We will now flip backwards. We'll now flip backwards. And I want to show you how we build the proof, how we got those tables, the excitations. Remember, you're now doing the projects, right? So you would have seen that there are 4 flip-flops. But in our lectures, really, we've only covered one, and we quickly did D. We covered SR in detail, right? How we got the characteristic table, the excitation table for the SR flip-flop. So let's just do a quick review. Let's do a quick review. So in the beginning, before the SR flip-flop, there was the SR latch. Remember, there was the SR latch, right? The latch was the one where we did case 1, case 2, and case 3. All right. To the latch, if we add two NAND gates and add a clock signal, right? The clock is for triggering. We then, because these are just NAND gates, and we can calculate what will happen if the clock is 0 and what will happen if the clock is 1. So we are able to come up with the truth table for the SR flip-flop. So this entire circuit with 1, 2, 3, 4 NAND gates is the SR flip-flop. That's the SR flip-flop, okay? I think everyone is now confident with the SR flip-flop, how we prove this, right? Because you may get in your exam to draw up the table from scratch. So take note of this, right? Okay, now that is the truth table based on that circuit there. We got S star, R star in the middle. This is just a review of the lecture. The first 20 minutes I'll just do a revision. Okay, now this truth table, if you look at it, there's SR, the inputs are S, clock, and R. And the outputs are Q and Q bar. Okay, fair enough. All right. So from here, from this truth table, we are able to reduce it into this in terms of looking at what the next state will be, what the current state is and what the next state will be. So clock, S and R, and what the next state will be. Because over here in the first truth table, we were saying terms in terms of memory. We're using descriptive words. We're using descriptive words, not used memory, reset, set. But we were not using formulas. So now we have converted this into a formula-like truth table. So that's the truth table. After the truth table, we are able to extract our characteristic table, right? We know what our S and R are. We can try all our combinations for Q and we find out what Q star is. So this is how we got the characteristic table. Do you remember how we derived the characteristic table? It's just from here, guys. So if S and R are some particular value, Q star is equals to Q. Qn plus 1 is equals to Q. So that's the characteristic table. Then from the characteristic table, we reduced it. We just reshuffle this. We take this column, put it this side, and we find out what our S and R are on the output. And we reduce it, and we were able to get our excitation table. From the characteristic table, we are also able to apply the Kano map and get the particular equation. Okay, everyone happy so far? So that's the SR flip-flop in detail. We did this about 4 weeks ago or 3 weeks ago, 3.5 weeks ago, right? Okay, that's the SR table in detail. This is week 12, right? We're in week 12. We did this in week 9, yeah, 4 weeks ago. All right, okay. Now let's look at the SR latch was here. That's the SR latch. That's the basics, right? SR flip-flop, characteristic table. Now the D flip-flop. How do we get the D flip-flop? Basically, we just take one input, we put a NOT. So basically, R will always be the opposite of S. R will always be the opposite of S. Can you see that? Right? So that's a new flip-flop called the D flip-flop. You've got the clock still there. So now your inputs are only D and clock. So if we take our characteristic table, if we take our truth table, right? This is again, we've done this in class, that's why I've written it. If we take our truth table from the SR flip-flop, we copy it down, right? The SR flip-flop. Now, our R does not exist anymore. So R gets cancelled out. right? And also, before r gets cancelled out, we note that this line does not exist. If you look at it, our s and our r will always be opposites of each other. Can you see? If s is 1, if d is 1, s is 1, r becomes 0. If d is 0, s is 0, and r becomes 1. So, is there any chance of these two becoming the same? No, never, because of this NOT gate, right? So, therefore, this line here gets cancelled out, this line here gets cancelled out. This is just a copy of our D flip-flop, of our SR flip-flop truth table. These two lines get cancelled out, and our R gets cancelled out. That becomes the new D. That becomes the new D. This will now become the new D. Okay? So, we now have a new truth table which is reduced. So, we have clock, we have D, and we have Q star. Clock, D, and Q star. That's our new truth table. Right? Okay. Now, from here, let's just redraw some things. After the truth table, what is the next truth table, my friends? It's the characteristic table. So, the D characteristic table, and you already know this because you've been using it. So, basically you've been using it, but I want to show you the proof. Okay, the D characteristic table is basically, it will have what? What will it have? It will have Qn, right? Qn. Some people call it just Q, right? And what else will it have? It will have D, and our output will be Qn plus 1, and sometimes in other tables that's referred to as Q star. So, how many inputs over here? Can you see there's 2 inputs? So, therefore, we do a combination. We do a combination. We have 0, 0, 0, 1, 1, 0, 1, 1. Yeah? Now, let's look at our table, this one here. I'll place that up and this one down. Okay. Now, if D is 0, this becomes D. Oh, I wrote it over here. I rewrote that particular table cleanly over here. If D is 0, what is Qn? Plus 1. What is Q star? If D is 0, Q star is 0. If D is 1, Q star is 1. If D is 0, Q star is 0. If D is 1, Q star is 1. We don't even look at the clock line. So, that's how we got our characteristic table. Right? Makes sense? Yeah, it's all the same thing, right? Okay. Now, so basically what can we say about this? What can you say about Q star? Q star is equal to D. Yeah? Q star or Qn plus 1 is equal to D. Alright, now let's look at the next one. What about the D excitation table? In the excitation table, let's go to the definition. You have your current states and you want to know your flip-flop input. So, you've got Qn, you've got Qn plus 1, and you want to know what is your D. 0, 0. So, we've got 2 inputs now in the table, 0, 1, 1, 0, 1, 1. Now, D. Let's now look at this part here. Let's look at the upper part. All right. Okay. So, if Qn is, so let's just to make you guys feel comfortable, that's Q. That is sometimes called Q star. All the same. All the same. Sometimes they call it Q and Q plus. Some textbooks. All right. If this is 0, let's look at this 0, 0. This is 0. This is 0. What is D? There will be 0. If this is 0, Q star is 1. Q is 0, Q star is 1. 0, 1. D is 1. If Q is 1, Q star is 0. D is 0. If Q is 1, Q star is 1, D is 1. There we go. That's how we did it. Simple and straightforward, right? Okay, let's now move to the next round. Okay, let's move to the next round. Okay, so if a question comes, how do we convert the D flip-flop, the SR flip-flop to D? What do? All you do is put an AND gate. Now, let me give you another question, the other way around. You are given a D flip-flop. You want to recreate the SR. You're given the D flip-flop. You want to recreate the SR. Right? So what would you do? Okay, let me expand on that question. Because the D, the input is there's only one input, right? Okay, what if your D flip-flop was given as the upper diagram, not the lower diagram? Basically, what you would do is, you could disconnect the NOT gate, right? Disconnect the NOT gate, all right? And basically just have an individual input into the R, okay? All right, now let's look at the JK. Let's look at the JK flip-flop. Okay, can you see this looks just the same? All right, now here's the difference. That's your JK. So if you look at it so far, it looks exactly the same as your particular, it looks exactly the same as your, it looks exactly the same as your SR so far. Yeah? Okay, now here's the difference, guys. That's your JK flip-flop. That's your JK flip-flop. That's how it looks like. That's how you build it. So in the middle of it, I want you to notice, in the middle of it, I want you to note that that you still have your original SR latch. Can you see the original SR latch is still there? The SR latch is used everywhere, all right? Okay, now, let's now get ahead and let's try and work this out. Now, again, once again, we just take some notes over here, right? Some sideline notes. If you have a NAND gate and you have 0 and you have X, the moment you have a NAND gate, what do you do? 0 NAND X will always equal to 1. Set? Everyone happy with that? We did this a while ago. And if you have this, we have 1 and you have X and you have a NAND gate, right? So 1 NAND X will always equal to X bar, yeah? Some basic rules, all right? Now let's draw our truth table. Let's now call this guy, let's call this point here, I don't want to use the thing S star. S star means next, eh? How about I say S circle? At this point here, R circle. Alright, okay? Everyone happy? S circle, R circle. Okay? So let's have your clock. Your inputs are clock. Alright, let's for your inputs are clock, J, K, S circle, R circle. What else? Q, Q bar. All right. Okay, good. Okay, now let's start off with some notes over here. Let's some calculations. Number one, if clock is equal to 0, what can you tell me about that? If clock is equal to 0, then what can you say about S circle and R circle? Then S circle will equal to, if clock is equal to 0, what can you say from this reading over here? S circle will equal to 1, yeah? And R circle will also equal to 1. Hey, that's starting to look very similar to our SR flip-flop, remember? Yeah? So if clock is equal to 0, it doesn't matter what really J and K are. Yeah, J and K doesn't matter. We know that our S circle and R circle will equal to 1, 1. And remember, this here becomes what? The SR latch. Yeah, this becomes the SR latch. If you have the 1, 1 going in there, what do you add? This will begin. This will be in the memory state. Yeah, in the memory state. So we can just say this will be in the memory state. Okay, let's now look at the ones. 1, 2, 3, 4 ones. 0, 0, 0, 1, 1, 0, 1, 1. All right. Okay, and the way to write it down is Q will be equal to Q star, which is same as saying Qn plus 1. Okay, now let's look at 0, 0. Let's make another note over here, notes. Number 2, if you have clock equals to 1, then from our earlier exercise, if clock is equal to 1, what will S circle and R circle equal to? S circle will equal to J bar and R circle will equal to K bar. You guys remember this? So let's say if clock is 1 over here, 1 comes in here. If any input into a NAND gate is 1, the output is the bar. Yeah? So it will be J bar and K bar. So that point becomes J bar, that point becomes K bar. Set? Yeah? All right. Okay. Now, let us consider the case of 0, 0. 0, 0, right? The first line. So 0, 0, what will this become? S circle will become 0 bar, which is 1. Yeah, because S circle is equal to J bar and R circle is equal to K bar. So Qn plus 1 will be, Q will be equal to Qn plus 1, which is same as saying Q star or memory, right? Oh, I forgot, maybe I should have put this down. All right, okay, set. So everyone happy? Maybe we just say for this line here, it is note number 1. How about I put this in Roman numbers? 1, 1 double dot. Look at 1 dot, right? Okay, set. And we look at 1 double dot. Everyone with me so far? This will be happy? Okay. So that's from note number 1, because if that's 0, all that becomes that. If clock is 1, right, remember, for number 2, it's J is equals to 0, therefore S circle will equal to 1, and K is equal to 0, therefore R circle will equal to 1. Set. So everyone's happy. Now comes the complicated part. 0, 1. 0, 1. Let's do number 3 now. Number 3. We're considering this one. J is equal to 0, K is equal to 1, and clock is equal to 1. Therefore, J is 0, K is 1, 0, 1. Therefore, S circle is equal to S circle is equal to 0, and R circle is equal to, S circle is equal to 1, right? And R circle is equal to 0. Set? Everyone happy? That's just doing the bars, because we know when clock is equal to 1. Alright, everyone with me? So let's put that down over here. S circle is 1, R circle is 0. So with 1, 0, 1, 0 being driven in, what is the case over there, guys? What is the case here? Into our SR latch. 1, 0 results in set. Right? So therefore Q is equals to 1, Q bar is equals to 0. Oh, sorry, Q is equal to 0, Q bar is equals to 1. So we have a 0, 1. Right? That's known as reset. Now let's look at 1, 0. So maybe I just put the note number here. That's the note number 3. Now let's look at the next one. The next one is number 4. Okay, continue to fill that table up. Note 4. In note 4, guys, let us consider J is equals to 1, K is equals to 0. We're looking at this line here. We're looking at the third line. Sorry, fourth line. Right? We're looking at this line. That will result in S circle equal to 0 and R circle equal to 1. Yeah, everyone happy? Now, if we supply a 0, 1 to the SR latch, if we supply a 0, 1 to the SR latch, we get set. That's known as 0, 1, 0, 1, S, R to the SR latch gives what? Gives set. Right? So let's fill this up. That becomes a 0, 1, and that 0, 1 goes into the SR latch. Set means what? Q is equals to 1, Q bar is equals to 0. Set. So that's note number 4. That's from note number 4. Last one. This is the one way it differs. So far, have you noticed that really all of it looks fairly straightforward? In fact, let's just compare for a second. Let's just compare with our SR truth table. This is our SR truth table. 0xx, 0xx gives memory. 100 gives memory. 101 gives 0 to Q, right? 101 gives 0 to Q. 110 gives 1 to Q. 1 to Q. All right? Okay? Now the last one, that's where it differs. So in basic summary, what I'm trying to say over here, guys, is that basically so far it's hand in hand. SR flip-flop and JK flip-flop are the same so far, except for the last one. In the case of the last one, okay, maybe I'll just make a note over here. Q star in this case will equal to 0. Q star in this case will equal to 1. All right. The last one, 1, 1. What is the situation in our SR flip-flop? SR flip-flop, not the latch. 1, 1. If S is 1, R is 1. If S is 1, R is 1 in our normal SR flip-flop. Not used, invalid. It's invalid. All right? That's a major flaw in our design, if you could say. Right? That's a major flaw in our design. All right? If you look at our SR flip-flop, we have a situation where it's invalid, not used. Now, the whole purpose of the JK flip-flop is to now fix that invalid. That's what JK does. So JK and SR, line 0, line 1, line 2, line 3, exactly the same, copy-paste of each other. Right? Only in line 4, the invalid line, the JK flip-flop is able to fix that problem. Because you might have a situation where, what if there's some static electricity and the 1, 1 gets fed into your particular flip-flop? If there's some static electricity and the 1, 1 gets fed into your SR flip-flop, then what happens? You can have it can be a mess up, because after 1, 1 everything starts to mess up, right? So we now try and fix it. Let's now go about it. Okay, 1, 1. We are trying to fix the 1, 1. I'm going to pull a line over here, and we are doing note number 5. Note number 5 is very long. A lot of proving to do. Okay. Okay. In the SR flip-flop, if clock is equal to 1, right, and J is equal to 1 and K is equal to 1, right, we have invalid state. We say not used. Okay. Now, for JK, we start off with an assumption. We assume Because in JK the circuit is slightly different. Can you see there's another extra line of feedback there? We assume, we have to start off with an assumption, right? Q is equal to 0 and Q bar is equals to 1. Now let's label this gate. Let's label this one as A and B. Alright? Gate A, gate B. Alright. Let's say Q is equal to 0, Q bar is equal to 1. We have to start off with some particular point. Alright. I hope you can see your diagram in front of you. I'll fold this paper, place it that way. Okay. Now, for gate A, let's consider gate A. Gate A, what is the output from gate A, guys? There will be output from gate A will equal to what? Q. Oh, right? Q is equal to 0. Oh, for gate A it will be Q bar. All right, can you see Q bar? Q bar and J and clock, whole thing barred. Yeah? Can you follow what I'm doing over here? That input is what? Q, that is J, that is clock. All right. But Q is equals to 0. That is assumed. Right? And J is equals to 1. And clock is equal to 1 because we are trying to do this, fix this problem. And what else? So, and what else? What else can we say? Q bar is equal to 1. Set. So therefore, gate A in this particular situation will be, as we said, Q bar, J, clock, whole thing barred is the same as saying, what is Q bar, guys? Q bar is 1, J is 1, clock is 1, whole thing barred is equal to, whole thing barred is equals to 0, which is what? S. Yeah, S circle. Is that everyone happy with that? S circle is equal to 0. Now, gate B. Gate B. What is the output from gate B? Gate B is R circle. R circle is equals to what? What is R circle equal to, guys? That equals to Q, K, clock, whole thing barred. What is Q? Q is assumed to be 0, K is assumed to be 1, right? K, J and K is both 1. And what is clock, guys? Clock is assumed to be 1. That is 0 bar, which is equal to 1, and that is equal to R circle. Now, so that means this is, what do we have over here? We have, what are we feeding over here into S circle now? That's a 0. And what are we feeding into R circle? That's a 1. So what do we get? From the SR latch, if S equals 0, R equals 1, Q is equals to 1, and Q bar is equals to 0. Now remember that. Right, let's do another round. Okay? All right. Let's look at it at the next clock pulse now. I want to show you something. Something is changing over here all the time. We call this the second iteration. Now, what did we get in the last round? Since Q is equals to 1 Q bar is equal to 0 from last round. From last round. Now gate A. Gate A is what? What is the output for gate A? It's S, right? And what is the formula for gate A? We wrote it properly. Is equals to Q bar J clock, right? And what do we get, guys? What do we get? What is Q bar now? Q bar is 0, right? J is, what do we get for J, guys? J is 1 and clock is 1. Remember, how did we get to this problem? We are trying to, how did we get to this problem, guys? We got to this problem because